Hello everyone, my name is Chunang. I come from University of Electronic Science and Technology of China. And today I will present our paper, a tree-based approach for building efficient task-oriented dialogue systems. My presentation will cover the following aspects: motivation, algorithm, experiment, and conclusion. In recent years, the task-oriented dialogue system has attracted more and more attention in both academic and industrial communities, such as Apple Siri, Ali Xiaomi, and so on. It aims to help the user to accomplish certain tasks, such as restaurant reservation, flight booking, or business consultation, etc. The typical task-oriented dialogue system often implement a complicated pipeline architecture consisting of natural language understanding (NLU), dialogue management (DM), and natural language generation (NLG). The function of NLU is to transform the user's input into the form that the computer can understand. It usually has two main tasks: intent detection and semantic slot filling. The DM takes the output of NLU as well as dialogue context information to determine the corresponding actions to be taken by the system. A typical DM component includes two stages: dialogue state tracking and policy learning. In the last module, NLG, the system's responses are converted into appropriate statements in natural language that the users can understand. Different implementations of the above modules result in different dialogue systems. Existing methods are mainly rule-based and data-driven deep learning. Traditional systems are based on rules. In such systems, a set of domain-dependent rules are predefined, and user utterances are matched against the rules during the dialogue. Typical approaches to dialogue management are based on finite state models, where the user utterance trigger transitions between the dialogue states, and these states determine the system's response. The main advantage of rule-based systems is that they do not need training data, so that they have no cold start problem. Yet, such systems have a disadvantage of limited generalization ability. Moreover, the use of handcraft rules for the state and action space representations makes it expensive and time-consuming to deploy a real dialogue system. In contrast, data-driven approaches rely on training the data. For example, in dialogue state tracking, the generative model is built to learn the relevant joint probability density distribution from the training data and calculate the conditional probability distribution of all dialogue states. Furthermore, to model the dialogue state more accurately, the discriminative model, which treats dialogue state tracking as classification task, is proposed. In addition, with the advance of end-to-end neural generative models in recent years, many attempts have been made to construct end-to-end trainable frameworks for dialogue systems, and promising results have been shown. We all know that this data-driven deep learning method has better generalization ability, but it is data-hungry, requiring a large amount of data to fully train the model. Based on the above background, we propose a hybrid approach which leverages the benefits from both rule-based and data-driven approaches. Firstly, we define an intent slot tree structure to implicitly specify rules for the dialogue system at low cost. Secondly, based on the intent slot tree defined, we present a rule-based and data-driven hybrid approach for building efficient task-oriented dialogue systems where the domain-specific data is insufficient for full training the deep learning model. The system framework is shown in the picture. The proposed dialogue system consists of 3 principal components: mode selection, single-turn dialogue, and multi-turn dialogue. Mode selection is based on a joint intent slot model. It will output the result of intent recognition and extracted semantic slots. When the intent matches the existing intent slot tree, it will go to the multi-turn dialogue, otherwise go to the single-turn dialogue. In single-turn dialogue, a 2-stage text matching algorithm is used. The matching algorithm combines relevance matching and semantic matching for retrieving proper answers to simple questions or greetings, where the semantic matching is based on semantic matching model. While in multi-turn dialogue, the user will be guided in completing his or her tasks following the intent slot trees constructed. Now I will introduce the intent slot tree and how to build it. The corpus contains multiple standard multi-turn dialogues between the users and the robot. One dialogue represents one typical interaction scene that the robot helps the user in completing one specific task. As shown in this picture, a multi-turn dialogue can be represented as a tree structure in which green nodes represent a robot utterance and white nodes represent a user utterance. For each dialogue tree, we construct a corresponding intent slot tree. It can be seen from the picture. And the main process to form the semantic slot value of the user utterance of the white node and the robot utterance of the gray child node into a 2-tube and create the corresponding node. Intuitively, each white node is merged with its gray child node. It should be noted that the root node of the intent slot tree is different from other nodes, in that it uses the labeled intent instead of the semantic slot. In real task-oriented dialogue, users often have simple questions, which are frequently asked in specific domain, or even they just give greetings. In that case, the system may just give the answer directly. Toward this end, we propose a 2-stage matching framework for retrieving the matched questions in database. In the first stage, a group of relevant questions are retrieved through relevance matching. In the second stage, the similarity between the retrieved questions and the user utterance are computed using similarity matching technique. Finally, the overall score of each retrieved question is computed by combining the scores obtained in 2 stages, and the question with highest score is selected as the question of best match. In multi-turn dialogue, the dialogue proceeds following the path of the intent slot tree established from the standard corpus. It consists of 2 steps: start, point location, and tree matching dialogue. In the mode selection, we have obtained the intent and semantic slots, as well as the matched intent slot tree. Since the user may give more information, we need to locate the start point in the tree instead of simply start from the root node, as shown in the picture. Traversal the root node to the leaf node if the semantic slot value of the current node matches the extracted semantic slot value. then continue to traverse downwards, and finally select the end node of the longest path as the start dialog node. Second, the tree matching dialog is used in the dialog process. For the question asked by the user, the semantic slot is also extracted and matched with all the child nodes of the current dialog node. If the matching is successful, the matched node will be used as the next dialog node. Otherwise, the rematching strategy will be activated. Like other pipeline-based systems, our dialog system faces the problem of error propagation if the NLU module does not correctly extract the semantic slots from the user utterance in MountainDialog. The above tree matching will fail, leading to the failure of the dialog. To circumvent this problem, we propose the following strategy. For each node of the internal slot tree, we maintain a weighting parameter and initialize it to 0. The weight is increased by 1 once the corresponding node has been visited. For the case that none of the children of the current node can match the user's slot, a single choice question is raised by the system. The options of the question come from slot values of the children with highest weights. Based on the new reply given by the user, the tree matching dialog will continue as usual. Now, I would like to introduce the experimental setup first. We extracted 1283 multi-chain dialog corpus and 2,000 frequently asked simple questions from dialog records in bank business consultation. From the corpus, we labeled 45 intents and 13 slots, and for each intent, we built an intent slot tree. Evaluation matrix use accuracy and task finish rate. Accuracy is used to average every module, and task finish rate is used for the entire system. We use the open source toolkit ConvLab2 to build two dialog systems as baselines. The first, named baseline rule, is mainly based on rules, and the second one, named baseline learning, employs deep learning method for dialog state tracking. Table 2 shows the performance comparison of baselines and our system. As can be seen from the table, our system shows the best performance among the three systems. Compared with baseline rule, our system achieves a accuracy gain of 4.67% for DM module and 7.07% improvement on the task finish rate. Compared with baseline learning, our system achieves gains of 13.57% and 15.46% for DM accuracy and task finish rate, respectively. The inefficiency of baseline learning system is due to the fact that there is no sufficient labeled training data to fully train the model. To demonstrate the effectiveness of rematching strategy, we compare the performance between our system and the one without rematching strategy. As can be seen from Table 3, the task finish rate of the system with rematching strategy is significantly higher than that without it. We notice that the average number of churns of our system with rematching strategy is larger than that without it. This is because that during the rematching process, the system raises single choice questions to the user, leading to the increase of the number of dialogues turns. Whereas in case of a system without rematching strategy, the system just launches the out-of-domain process, which directly ends the whole dialogue. In this paper, we present a practical way to develop task-oriented dialogue systems under a limited amount of training data. First, we define an internal slot tree structure to implicitly specify rules for the dialogue system at low cost. Secondly, we present a rule-based and data-driven hybrid approach for building efficient task-oriented dialogue systems. The proposed approach leverages the benefits from both rule-based and data-driven approaches. Future work is expected to extend this method to deal with more complex tasks, such as cross-domain dialogue applications. That's all. Thank you.